how do you put that on?
Okay, and so what we got to do is we will switch over to a screen share. Right here. And we'll share the entire desktop. Go back to routing. Lectern PC, send to all.
That's on my
Desktop. Start screen share. Infinite windows. And PowerPoint. You want a terminal open? What I always do. Yeah, what I always do on a Mac is I hit Command and Space. It brings up this little search guy.
Okay, what's it called?
Terminal. But I'll bring one up for you.
And so then I can log in and Stampede from there.
Yes. And it's Apple Plus to make it big. Make a You can draw on it.
Just make it big.
Is that big enough?
Yeah.
So you can SSH to Stampede from there. There's your presentation, and what you can do is Command Tab right in between them.
Okay. Do another 5 minutes. Okay. Cool.
Let me know if you need any help.
I really don't want to. I'll figure it out.
I know what you mean. You do? No. You don't? You still don't know. You need to figure it out. Wow. You wait, brain racing. Yeah, you should. You should.
That's just the allocation for the RU side. But I'm assuming here we go. But now I've got to do it now.
I mean, if not, I can. What does do you, or anyone use the method?
Apple, I like mock Pearson method.
Do you use the method? Oh, sorry.
Is it like online?
No, do you use the method? Where's the console? Which one is that?
It's a. But like the math lab itself wouldn't have an allocation. Yeah, but you can run it. Because you need allocation.
Yeah, you just use SSH, so whatever. Well, that's fine.
Well, you're doing like SSH into your account, but your account is tied to that's an allocation. But I'm assuming like when you go to use the method, you're like, oh yeah, of course, when it's the allocation.
Yeah,
That's too soon. Figure it out.
Urban Dictionary.
Yeah.
What did you Urban Dictionary specifically? Did you specifically go down?
Yeah.
Oh. I want to see what it's saying. There's one that says.
Yeah, that I can see why that would be lost.
you like not having to start local. Just blend it back. It's like a sugar daddy, not actually
Not real sugar, but
like, you should pick that up. You said Lola is going. Yes. Right.
In my school, they take pictures of me a lot. Did you not give me whole area? Wow.
yeah. Yes.
That makes sense. It's like you were actually born and you can fly. Like something to see that.
You don't see how we got there? The bubble crumble?
Hello,
No.
let's get started. My name is John Kaz. I'm going to talk to you about MPI, the Message Passing Interface. On our systems, this is just about what probably 95% of the code's used to do parallel computing. I think Doug covered a little bit of this, just mentioned what it was. Okay, just a quick overview. Let's see if I can use this. I guess I don't have a laser pointer, so I'll just use the mouse. Okay, so shared memory. You should have just learned shared memory is within a node, within one system image. That's primarily on our systems OpenMP. A few people use pthreads. There are some other shared memory computing libraries that aren't as well supported. So MPI is what we're going to talk about today. This is for distributed execution on several different systems. So you can think of each node in Stampede, if you've already had the tour, you've seen it, as a system. And usually we run multiple MPI tasks on one node. It could also just be a collection of workstations if you've got it set up correctly. There are many ways you can distribute MPI across the nodes. And these are more exotic systems over here, or I should say more exotic methods of communication. None of these have really caught on that much. There have been several efforts to sort of go to the next level and make a parallel language that's easier to understand and easier to program, but MPI is still hanging in there because when they go to these languages and they look at their performance, pretty much sucks. So people go back to what they know, what they've spent years developing their code on, what works. So just a quick history, MPI is 25 years old. So we really do need something new. This is pretty archaic. When it was developed, CPUs had single cores. Most nodes had one socket, so one CPU. So that was it. You had a system, it had a processor on it, and it had one core, and it communicated. Now, we've gotten much more complex systems. We have more than one socket. Each CPU has more than one core, so we have these different levels of parallelism and different ways to compute things and communicate. And so MPI pretty much has this one method of communicating from task to task. And during the talk today, you'll hear me refer to tasks. MPI creates tasks. You can think of a task as a computer process. And the task can be multi-threaded or single-threaded. So if it's multi-threaded, then it would be using MPI with something like OpenMP or pthreads. This is just a quick look at how MPI has changed. It's changed fairly slowly. Whoops. Okay. Don't click the mouse. Back in the probably to the late 90s, even though this says 94, 96, it wasn't really to the late 90s that the standard added some functionality to include parallel I/O and one-sided communication and lots of features we're not going to cover here today. Today I'm just going to talk about the very most basic ways to use MPI, which are all present in this first version of MPI. And just recently the standard for MPI 3 came out, and as far as I know, none of our libraries support everything yet. This is similar to the way compilers advance. When languages add new features and a new release comes out for Fortran or C, or there's a new template library for C++, it usually takes a few years before the compilers begin to support all the added features. So this is just a simple diagram of how people usually turn their codes into MPI codes. So they start out with a serial code. They've written a code to do some sort of numerical simulation, and then usually the reason they go to MPI or parallel processing isn't so much performance, it's almost always memory. They don't have enough space on one system to simulate everything they need. There's too much data. And so they have to scale out to get more access to more memory in more systems. I mean, as a side effect of this, they also get more performance because they have more CPUs to run. So in general, what happens is they take their sequential application, they have to go through very carefully and look at how it executes and decide what parts can be done in parallel and what parts have to be synchronized together. So in general, there are a lot of small operations that are all repeated on all the different tasks and all the different cores. And then there are synchronized operations where you split the data up. I don't know if Doug talked about data decomposition. No? Yes? Okay, I should have had a slide on that. I thought he was going to cover a little bit of that. But basically, if I've got this huge data set that won't fit on one processor, I split it up across all the processors.
Oh, yeah.
Okay? And so then, everybody sort of does the same thing until they have to process the data. Then they're usually doing the same thing, but on a different piece of the data. But a lot of times, the data you're working on also needs information from data on another processor. And that's where MPI comes in, because the only way you can find out what's on this other core is to communicate. And so what you'll do is you add MPI calls to move data around, and add MPI calls to synchronize your program with the other programs. So this is just a look at what an MPI program might look like. And pretty much the way most people run MPI, I'll get to this in a second, is it is the same program on every core. There are if statements and switches in the program so it can figure out which core it's on, so it knows which data it works on or what task it's supposed to do. And so in an MPI program, everything before the initialization of the MPI environment, there is no communication. Basically, you have to sort of start MPI up, like turning on an engine, before it can begin to communicate. And then when you're done, usually at the very end of the program, you shut it down. And in the middle, where all the work gets done, that's where you're mixing sort of sequential computation and parallel computation. And this is what I'm talking about, this first mode of execution. Probably 80 to 90% of our MPI programs have this technique, where all of the executables started are the exact same executable. So it's the same code on every core. But every once in a while, people have special needs, or they have a different way of doing things in parallel. Usually it's some type of task parallel, where each executable is doing something pretty different, fairly different. And they'll use this second mode, which is a bit more complex to program for and a bit more complex for our systems to start up, where every task might run a different program, or say the first 10 run one program and the next 6 run a different one. And you don't see this mode of execution as much. I'm just sort of letting you know that it's out there. If you ever get into parallel programming and you see somebody running something very strange looking, it could be this type of program. But the thing is, all of these programs, once they initialize their MPI environment, they're all in the same group. They can still talk to each other. And so this is probably the most important concept of MPI. Once you start all these programs up and they initialize the MPI environment, they basically registered themselves to each other. So one program starts up and says, well, I'm task 0. Another one starts up and he coordinates with the other tasks, and it's like, well, I'm task 1. And so basically they've identified themselves to everybody else, and they know how many other tasks there are, so they can begin to communicate. I mean, so this is important when you're writing a program, because usually at the very beginning, your program has to decide, oh, am I one of 4 tasks? Am I one of 20 tasks? Am I one of 10,000 tasks? And if I am, what part of the data do I work on? And how do I interact with these other tasks? And so for every MPI program, there's this one big group that encompasses all the tasks. That's MPI COM world, because it is the world for that program. Another key component, though, is you can make subsets of this world. So let's say you're doing some processing on a 2D grid. So I've got rows, and columns. I can make subsets along each row and each column. So when I only need to do work on a row, I use a different communicator, and I just talk to the other tasks that I need to on that row. So you can create a hierarchy of these communicators. Okay, now I'm just going to cover some basic routines. These are the routines you'll see in every MPI program. And MPI itself stands for the Message Passing Interface. It's really a description of an API. It's an API for libraries that send messages. Even though I'll talk about an MPI compiler, what it really is a wrapper that uses regular compilers like Intel, PGI, or GCC, and links in all the libraries you need to have to make MPI calls. And so for any MPI program, for it to be considered an MPI program, first you've got to include something that lets it know what are these function calls, how does this work. I think most of you are very new to programming. So you had a little bit with Fortran and some C. So you're a little familiar especially in C, you have to, if you're going to use a function somewhere, you have to define what that function returns or how it operates. And that's what's buried in these include files. It just defines some constants that MPI uses, some data types that MPI uses, and how these functions work. In other words, what are their arguments? What do they return? And so to start up any MPI program, you have to initiate it. And this part here for C, it's a little bit different. Whoops, don't click the mouse. It's a little bit different than for Fortran because in C, it always expects arguments. Fortran doesn't expect command line arguments. And so you basically have to repeat the command line arguments for the C program here in the initialization so that they're broadcast to all the different tasks. So every task sees the same input arguments. And so after you've initialized the environment, somewhere in the middle here, you'll have calls. So you'll do some computation, you'll do some numerical work, and then you'll call some MPI functions to coordinate with the other tasks or move data. When you're done, you finalize. And finalize shuts down MPI on all the tasks. I think I just said most of this. These most basic ones, the size tells you the total size, the total number of MPI tasks, and the communicator can be MPI COM world, that gives you everything, or it can be one of these sub-communicators if you created a smaller one. Because sometimes you want to know, okay, what's the size of this local group? And so size is important to know how big it is, and the other important call is MPI COM rank. Because you need to know your place. Here's a group, it's like, here's a list of things. You need to know at what place you're in the list. So you've got to have a name to speak with someone else. And to know who to speak with, you need to know their names. And these are the calls that give you that information. And the W time thing, MPI implements its own timer because, well, one of the issues is the cores might be running with slightly different clocks. And so W time tries to make sure the difference in timing between the tasks are consistent. But it's local time. So a W time on one task and W time on another task could give you different numbers. So all you ever do is calculate the differences between the times. And so here's about, well, this is a serial program, Hello World. You probably saw this in your C session. I mean, you've got to do Hello World for just about every language that's out there. Yep. So if you want to make it parallel, you need to add some MPI. And so all we've done here is initialize the MPI environment with the init, figure out where I stand in this environment. What's my task's ID? What's my name? And then here, even though I don't use it, just figure out how many tasks there are total. And print it out. Okay, so hello world. That's about the simplest one we can do. And we're going to do a simple hello world example in a couple minutes. So here's what I was talking about compiling earlier. On any cluster, you'll see these compilers. They'll call them compilers, MPI-CC for C, MPI-CXX for C++, and MPI-F90. Sometimes you'll see MPI-F77 for Fortran. Now, on most systems, if you go look, these are wrapper scripts. They're shell scripts that basically set up all the libraries, lets the compiler know where all the libraries and include files are, and then it compiles your code. But generally, you use it just like a regular compiler. All the same arguments, -O, -G. I think the Invapage the Vapage compiler links in maybe 3 or 4 libraries. It's not a whole lot. I mean, there's one for InfiniBand because we sit on top of specialized hardware. There's the MPI library itself. And then I think there's another optimization library for shared memory communications within the node. Because most modern versions of MPI, when they communicate within a node, they use shared memory segments. So they use memory buffers to exchange the data. In the bad old days, they actually went to the network card and sent their data there, and then the process on the same node got it from the network card, which is really, really slow. So it's not a whole lot of libraries, and you can compile by hand. I mean, you can set it all up and just compile everything explicitly by hand. It's just much easier to use these compilers. And every once in a while, we get tickets from people on our systems who are like, hey, I can't build this, and usually they're trying to build by hand instead of using our compilers. So in a minute, we're going to do an MPI example, but I'm going to try to do this interactively. So we're going to use, have you used IDEV yet? Anyone use IDEV?
They talk about it.
Okay, well, we're going to use it, and I've got a reservation, so I hope it works. But I was just going to show you what a batch script is. Anyone talk to you about a batch script? Okay, so I'm just showing you an example of a batch script. It's fairly simple. A batch script just tells the system how many processors you want to run on, what's the name of the job, what's the output, how long you want to run, what partition. But we're not going to do that. This is what we're going to do. So if everyone's got a terminal up, can you log into Stampede? And once you get going, I'll bring up my terminal. So if you're on Stampede, type IDEV. Let's see what happens. Just type IDEV enter. And it should ask you about a reservation. If it does, say yes or Y or IDEV, IDEV. Yeah, just this. The little percent is the prompt. That represents the prompt. So yes, yes. Yeah. Well, we reserved 10 nodes, so we might have more than 10 people, so someone might get blocked out. Yeah. There should only be one reservation listed. You got 2 reservations? Oh. Hmm? It's gonna sleep until it comes on.
What is it?
Go ahead.
I think I figured it out. I was trying to think about why we were doing the IDEV.
Okay, so let me explain. We're doing IDEV to get access to a compute node. We can't run parallel programs on the front end. We have to be on a compute node. IDEV puts us on a compute node with a proper environment to run things in. One of the issues one of the reasons I got the reservation is we only have a subset of nodes set up for compiling on the compute node, the development queue. And usually it's pretty packed. So I asked for a reservation for 10 nodes, hoping you can get on there. Then you can compile on the compute node. Otherwise, you have to have either 2 windows up where you compile on the front end and you run on a compute node if you're in one of the other queues, or you just submit batch scripts. Okay, people on? Okay, so you can untar the file. You should just enter this command. You should end up with a directory called MPI examples. I don't have a laser pointer. There's a space after the F. There's not a space between the tilde and the train 00. In Linux and Unix speak, when you do tilde and then a name, it means that user's home directory. So tilde train 00 is the home directory for the user account train 00, which is sort of our base training account where we stash all our exercises. Sure, go ahead. No, you don't. So the percent sign is the prompt. Like I'm showing you what you see on the screen. So don't type the percent sign. Sorry. It's not the percent.
When you hit IDEV, what do you type? Do you want to use your
Just hit return. Say yes. Yes, you want it.
So is parallel hello supposed to run straight?
Well, so no, the only difference between these two is hello is just a serial code. I'm showing you that the MPI job starter will start multiple serial codes. Parallel hello is actually an MPI code where it gets its task. And I'll go into the next one when more people get done, but I've got snapshots of the code here, or you can just look at the code, just cast the code. And I'm just trying to show that the other one's an MPI code, even though they're basically doing the same thing. In the next example, we'll do communication.
Do we do all? Do we type it all? Or do
Yeah, he said.
Type what? Yeah, go ahead. ibrun./hello. The / is there because you don't always have your current working directory in your path. So if you type /, it'll find it. There's a space between tar and X, and there's a space between F and the tilde.
That's supposed to see another space.
16 times? Yeah. Yeah.
And then shut down.
And then the task. Hello, task 8, task.
Yeah, so when you run the parallel one, it tells you what task it is, because that's the MPI job. When you run the other one, it's just a serial program. So ibrun just starts the same program 16 times. And you see it 16 times. Sorry, you see it 16 times because there's 16 cores on a node, and so by default, when you enter the command idev, it asks for one node with 16 MPI tasks. So when you use ibrun, our custom starter, which sets all the details up for you, it'll run 16 tasks. What you can do is you can export an environment variable called my underscore n slots, all caps, equal to another number, and it'll run fewer tasks. Or you can do ibrun-np4. It'll do 4 tasks.
So, type this.
Yeah. Why does the task report like error when
Okay, so the thing about what's happened, I initialized the environment. I figured out what I figured out how to then I created some information. So the only thing in synchronization goes well, it's not even, there's no synchronization. In other words, when I initialize the environment, as soon as all the tasks that I handle and run, MPI is returned. So then 3, 4 functions that are called, they're not synchronized between tasks. So whoever prints out is whoever gets it first.
Right, so when I do think that you guys
It doesn't have to be, because if task 0 is coordinating all the other tasks, he may be slower. But in other words, they should all finish
Type it out.
and then it's a portion.
I mean, you have to type it.
Now there's a command I'm going to mention later.
Now
called
it's
barrier.
it's not dash
The
0.
barrier is
It's dash
exactly what it sounds.
dash
Everybody hits the barrier and stops until everybody hits.
So could you really could each core at a different cost?
No one ever Twitter was here. That's the one.
Well, they might be running
Do you have any idea how many geeks are on Twitter?
I mean, it's just, it's how you
There's nothing about
Did you know that was hard? Did you do the
Let's
hard?
say-
There's nothing that like you to like slide ideas.
and I said,
It's not all like
1 to 1 million times my
I don't know
task.
what it does. But I like it.
Then I probably see the word, right?
Yes. Yes, that's actually true. Actually, do have that. I actually literally do have DMs like that.
Communication.
Yeah.
See some things go in order. There's another example of blocking.
They don't understand. I'm like, I'm gonna
Everybody
screenshot it and send it to all my friends.
There you go. Now go to the direct. Go to
This is why
Oh, yeah.
these programs you have to think of when you're doing communication.
So you're watching finding
careful how you
source
think
code.
about it. Because you're thinking linearly and you're thinking, oh, well, 0
I think that's
1 and 2. But if you
good.
build
Now do it. If you
communications,
do,
it's going to do that.
do a list.
You're gonna get to something called a catalog.
See, now you've
I'll
got.
show a little example of that. And that's basically,
Now,
the two
now
concepts,
we did.
the two tasks are both trying to talk to each other, but neither one's receiving their communication so well.
How did you know?
So it's like two people yelling at each other about listening. So has everyone gotten something or?
Do you guys like teach free courses and have to pay for them kind of employers?
Well, no, we actually teach a lot of, like 1 and 2 day and 3 day.
Like if I just wanted to like come to like a TA in town or whatever.
We do a lot of that. And we have, now, the only one we really charge.
There's a space. I
Is
should
the Summer Institute.
PowerPoint formatted to that one. But, I mean, there's a space.
Throughout the year, we'll teach 1 day, 2 day, 3 day courses all the time. We can solve.
There you go.
And how long does it take for me to, do more than like hello?
Well, I mean, it depends on how you define it. But the short answer is. The short answer.
I'm waiting to hear what he says.
The short answer, when you finished algebra, would you say you were managing? But you were beginning to accomplish it. And then you took algebra, you can make a career out of this. I think realistically, we have a curriculum that involves more serious courses. You could begin to take this as an undergraduate. I think realistically, after 2 or 3 courses, you can do more meaningful work. If you really, really enjoy this stuff, people like him, coach, we have a competitive scene.
Yes, we do.
Oh my gosh.
We are the world champions 2 years.
2 years running. We're going to compete again this year.
And I'm serious, and you get to travel to the competition, you stay up all night.
Is there like an age limit to children?
Undergraduate or high school? So far, I don't think we've seen a high school team not in the competition we're in. You can't be a graduate student. There's no age limit. It's just academic classification.
Okay.
And you don't have to be a computer science major.
No.
It's pretty cool. It's really, it's a lot.
I'm gonna actually.
You
Are
have
you
to-
gonna be on? Do you have
You
to
have to build the
compete to solve it the fastest way?
So the way this competition works is we're given applications like now. We were given applications about a month ago. And the students work to learn the applications and how to manage the cluster. So we build a small cluster. Last year, I think our cluster had 14 nodes. So we build a small cluster. We teach the students how to admin the cluster, set it up, manage it. The students pretty much learn on their own how to run the applications, run test cases through there. They usually don't have to do a lot of parallel programming, but they sort of have to understand it to know how things work, how to make it run faster. In other words, should I run on 24 tasks, or should I run on 12 for twice as long? Should I run on 8 tasks with 3 threads apiece?
No, he was like screaming.
So they have to learn how the science works too, because they get judged on their understanding of application to competition. Now the biggest thing is, we show up, we help them set up the computer, and then the competition starts on Monday morning, and then for 3.5 days it runs, and we can't touch it, and we can't give them advice. It's over. Our interaction is basically, here's some food, good job, let me know if you have a problem, and we'll talk to the judge, but they pretty much have to know how to do everything on their own.
Yes.
Yeah. It was a lot of fun.
Yeah, that just means that. What that means is,
So,
you're waiting for access. See,
there is not a programming challenge.
And the reservation is just 10, so they got in ahead.
There are some other
And,
sort of HPC high performance computing events that have a programming challenge or something like a hackathon. I think it exceeded last year.
Okay, you got it.
Cluster conference, Mike.
Okay.
There's a conference that has many different parallel tracks for parallel computing.
I'll bet, literally.
International
but there's
parallel
you and one other person sitting
distributed
waiting.
It's a big meeting. It's a hodgepodge of like a lot of small meetings, and I think they have.
See, he just reserves 10.
But it's not quite like most of the hackathons.
Yeah, that's not an easy, like, I'm guessing.
There's one on YouTube.
Yeah.
No,
We should do it
well,
together. I think
you're developing, they give you a problem, and you have to write the code in a certain amount of time that provides a solution.
Yeah.
Or say it runs quicker than everybody else's.
So it trains teacher hackers.
If you want to be a hacker, basically learn Linux kernel.
Yeah.
You don't have.
I'll tell you that right now.
Like, so the people who are on the super team, like, they said they're not necessarily like CS majors.
Well, most of them are, but they don't have to be.
Yeah. The VCEs.
Do you like them to try
The
out?
VCEs.
I don't know how they.
Yeah. I mean, and our leader this year, he's a biologist. I mean, he does a lot of computation.
Yeah.
John, no, well, so John's on the committee this year. John, he was lead advisor last year with Carlos was. I was lead advisor 3 years ago. John was lead advisor 2 years ago. But there are about 4 of us in HPC who basically mentor the team and set it up and try to choose students March, because we have to have a submission in by early April. So you have to write a proposal and compete with other submissions to get selected. So there's 6 members on the team.
So like, do I need to try out like, I don't know how it works, so like, or it's just cold, like I submitted my code and it doesn't pass.
No, well, so for this, we usually post something on our website. I think we tried flyers before. We didn't get very far with that. We have some computing classes where they announce to the students. The problem is a lot of these classes, it's mainly seniors. And so if they're a senior in the spring, they're probably graduating in the fall. You have to be an undergraduate in the fall. But in word of mouth, the students who've been in
Is
it.
the competition only in the spring?
No, so the competition is in November. In other words, supercomputing is the second week of November every year.
Oh no, so like I won't be able to compete.
Sorry,
when
I don't know how to do
graduate.
it.
Well, so, and the other thing, and we tell the students who apply, be aware that we're going to compete in the second or third, I think it's the week before, or 2 weeks before Thanksgiving. And so usually, that's towards the end of the semester, and things are getting intense. And we try to tell them, it's like, look, you're going to have to spend a lot of time on this, it's going to be hard. And then towards the end, we'll meet, usually every week, at least 1 night a week, but they'll work on their own. So I have Skype sessions up and talking back and forth, trying to figure out.
How do I get on problem? I don't know my. And they.
It's intense, and then when they do this competition, part of the competition lasts for 48 hours straight. So there's someone at the computer pretty much for 48 hours. So they go in shifts. Huh?
It's like for what's an exam, like in the there's like this exam that, well, I don't know if it's but UT the exam. It's like the one-name competition, so it's like, it takes all like, these really hard math problems, it takes 8 hours.
Yeah, it's like-
And if you're like the top 5%, I don't know. I usually do number 1, but,
What you win here is a certificate. You get a little piece of paper, and they take your picture, and they put you on the website. Okay. Yeah, you get this for a year. You get to go. We're the best. And they've lit the tower for us twice now.
Oh, they like the towers for it?
Mm-hmm.
What does that mean?
Light the tower?
They like the tower.
They make it orange. They light it orange. There's a website at UT. You can go to the website. Why is the tower orange? And it'll list. We made the tower orange today for this, or we made the tower orange today for. It's like this team won, or this accomplishment.
Orange every weekend.
Yeah, I think they do it quite a bit.
I'm like, dang, how much time did you can't be the football team.
Maybe next year. Okay, I'm going to move on. All right, point-to-point. Point-to-point communication. So, Basically, point-to-point just means one task is talking to another task. There are two tasks involved. I just spoke to you. Actually, what I'm doing now is one-to-many. We'll cover that in a minute. Point-to-point is if I'm just... Okay? Point-to-point communications. And this is what I'd say most of the MPI calls are, because you do a lot of local work and then you talk to your neighbor. You give them some data. Your neighbor gives you some data, then you can do some more work. Every once in a while, when you have to synchronize across everybody, that's called a collective communication. But first, let's get to point-to-point. And what you should get from this is there are many MPI calls that do this, so I'm just going to cover two. And one of them is what's called blocking, which means it sends the message and it won't continue until it's sure that the data it sent, enough of it is gone, that it can reuse that data locally. Non-blocking means as soon as it sends the message, it returns and you can do whatever. But you're not guaranteed that the data you sent is safe to change. And non-blocking receive means the same thing. Hey, I've received some data, but you're not guaranteed until you check that that data is safe to use. So the reason we have blocking and non-blocking is there are cases where you want to overlap communication with computation. Because a lot of the message sending might be handled by a different process, or it might be handled by some hardware. And so if I can just throw data at some hardware and then go off and do something else, and then I just come back and check to see that it's done, that's more efficient. And so most of these advanced codes, they use non-blocking communications. The blocking communication, though, is a little easier to understand. It's like, here, I give you this, and I don't go on until you actually take it from me. And then I know when I'm done, I'm done. I can go on and do something else. The thing is with blocking, it's very easy to get into a situation we call deadlock. I'm going to show you a simple example of that in a second. So here, don't worry too much about this. This is just what the syntax looks like. If you look at some of those codes you just unpacked, you can see these calls. The thing about the non-blocking communications, though, is you need something else, another call, and that's what this wait and wait all are, to check to see if they're finished. So let's say I send some information non-blocking, then I go off and do some computation, and then I want to change the data I sent. I have to make sure it's safe. So I have to call this wait. It's kind of like, let's see, what can I say? I give you something, or I just put it at your front door, and I run away. I don't know if you've got it or not, but let's say I can't do anything until I know you've received, and then I call you later. Hey, did you get it? You say yes. Okay, we're good. That's non-blocking. Blocking would be like I stand at the door until you open it, and I stick it in your hand, and then I walk away.
Where it is not like, so if I returns a data set and it's non-blocking, what is the doorstep for the next like function?
Well, so okay, so I send some information and it's non-blocking, or I receive some information and it's non-blocking. As long as I'm not trying to do anything immediately with that data, I can do whatever I want. I can go on and work on other data. I can send other messages. I can do anything. It's just, it's not safe for me to touch that data until I go back and check to make sure it finished. Yes. And that's what the wait does.
So where is that data stored when it's not being used by either thing?
So it's in transit. So technically on the computer what's happened is when I send it, it's copied to a local buffer to be sent out to another system, copied into a local buffer on that system, and then eventually it's copied into the process's memory space. So until I check it, it's in one of those places. It's either in my buffer, it's on a device buffer, it's on a buffer on a remote system, but maybe not in that system's tasks memory. And so it's in limbo. I don't know. Now, if it's a small message, odds are it was sent very quickly and it's done. But until I check, I'm not sure. And so this is just an example of communicating between two tasks, task 0 and task 1. I'm going to send a message, then I'm going to receive a message. And so since I'm sending a message here, task 1 has to receive a message because task 0 sent it. And then after task 1 gets it, it sends a message back. This is a classic MPI benchmark called a ping pong. Ping pong. I send it something and then it comes back. Ping pong. So that's pretty simple, right? But what if I had basically the same code for both? So here I'm saying this will deadlock because actually I would have reversed the order. I've got to receive here and I've got to receive here, but nobody sent anything. So they're both going to be waiting. If I switch the order, it's the same thing. If they're both sending, the sends can't complete until someone receives it. So this is called a deadlock. In a complex code, sometimes it's hard to find this. Your code just stops. You don't know where. You don't know why. That's generally when you fire up a debugger and try to figure out where it stopped and why. And you find out one task is waiting on something and another task either never sent it or it's waiting on something from that task. Like I say, it's two things at cross purposes. Okay, so for a non-blocking send and receive, you have a little extra thing in here, request, because you have to tag it somehow. You have to give it some piece of information so when you go to see if it's finished, you know which communication to look at. Otherwise, you might have 20 sends out there, and you don't know how to check which one finished. And so this little extra part at the end is just, oh, it's this request or it's that request. So when you use this wait command, you put the request in there. And you can get a status because you've also got this test. So it's possible you can send some data, go off, do some work, come back and test it, not wait. Because wait will block until it finishes. Test it and go, oh, it's still not there. This is a really slow system. I guess I'll go off and do some more work and come back periodically and check it. And these others, wait all and wait any. Wait all means I have multiple requests out there, and I'm going to wait until they're all done. And an example I have later will have that in it. Wait any just means, hey, let me know when anything's done, and once it's done, when that one's done, maybe I'll go work on some of that data, and then I'll come back and check to see if any others are finished. Okay, so we're going to do another example. Are you still on there?
Yeah.
Okay, so if you're still in your IDEV session, ignore the first two steps and just compile these codes.
How do you want to put your item?
What's your prompt say?
C55.
You're in your IDEV session. Otherwise, it'll say login 1 or 2 or 3 or 4. So you're on a compute node. By default, these sessions last 30 minutes. But since we have a reservation, it should be pretty easy to get back in. And those are the output, the names I gave it. You can name it whatever you want. Anyone run yet? Which one ran in order? Or which one output in what looks like order? Right. And non-blocking didn't, right? This is what we were discussing earlier. So I'm going to jump to the next slide. Okay. No. And so what's going on here is one is using blocking communications, and the way it's initiated sort of means it's going to be like dominoes. One can't continue until the previous one completes. The other one uses non-blocking communication, which basically means It just does its send and its receive, and it just waits until it gets some information, and then it prints. So for that one, you're not going to see output in order. You don't have it. Well, that's if you're already in the directory, you want the first. If you're already in the directory, type PWD. Yeah. So just ignore the first two. I put that up there in case you're out of your session, then you have to use IDEV to get back on a computer. Okay. So what's happening is in the blocking example, everybody receives first before they send except task 0. Task 0 sends first. So what happens is task 0 sends, task 1 receives, print something out, and sends something. And so the next task can't receive till task 1 until task 1 sends. And so it goes around the ring. And everybody prints after they've received their data. And so your output is in order. Now for the non-blocking, basically, no one waits on the send or the receive. They perform both operations, then tell it to wait, and then print. So there's no guarantee as to who receives their data first. And so that's why for the prints on the non-blocking, they're in a jumbled order. And so this is something you sort of have to keep in mind when you're writing a parallel program, and usually you're using non-blocking communications. This sort of automatic order you assume in your head may not happen that way. And so you sort of have to plan for this. In other words, if I want to print output in a certain order, I'll have to coordinate with all the tasks to make sure it comes out in that order. Let's say I want to write to a file in a certain order. Let's say I was writing all of this to a file, and I expected the data to show up in this specific order. Well, if everybody opens the file and just writes their data when they get it, then when you go to read the file in, it may look like garbage to you because all of the output is in a very jumbled order. Yes?
Okay, so you can do it in a random order and you can do it in like, I guess, software would want to do it in, let's say, 7 to 15 and 0 to 6.
So you can change how you started. Well, you see I started at 0 and I've got it set up so 0 goes to 1. So let's say I wanted to start at 7. So I could have 6 sent, 7 received. I wouldn't have to, well, I'd have to make sure I control the leak, because if I go to n plus 1 when I get to the end, that's where up here when you set it. If you look at the code, I don't have a code of slides. If you just look at the code, tap that C program, blocking. If you want to go in order, not blocking. Yeah, that's just CAT. Okay, so at the top, I said destination switch each task. And I make sure that the highest task I do knows that it goes to 0, not ends up 1, because it's everything. Okay, so then what you're saying, down here where I have this task ID equals 0, I can change that to task ID equals 6. Then it will still do the ring, but 6 will be the first one to send, so 7 will be the first one to send. So you'll see 7 through 15, and then after 15 you'll see 0, because up here you've already told the key that its destination is task 0. So the ring will still complete, it will just start. 6 will send, so the first output will be set. I mean, the main point I'm trying to make is you have to worry about the actual order of communication done, and that what you assume may not be true. Well, I've been doing this for 20 some odd years. That's just, I mean, it's. Okay. So now we're going to talk about collective communications. These are communications that basically include all the tasks in the communicator. It could be the world communicator, it could be a sub-communicator. So it's like me speaking to all of you, one to many. And generally it's one to many to one, many to many. And these are blocking calls. So every task that is part of the communicator has to hit this call before it can continue. So there are no non-blocking collective communications, well, until now. In the latest version of MPI, MPI 3, they have introduced a non-blocking collectives. But I haven't used them. I doubt they're in anybody's code yet. I'm not sure they're well supported. So we're just going to talk about the blocking ones. And yeah, this is an important point. So before you're just doing point-to-point, so it's like I send you this data, you receive this data. Now all of a sudden you're sending data in a lot of different ways, and so everything you send has to be matched somewhere by a receive. So it's got to balance out. If it doesn't balance out, sometimes what happens is it doesn't hang, but it causes parts of your memory space to get overwritten and your code does really crazy things. You get error messages you don't understand. So the simplest one is the barrier. The barrier just says, everybody stop. Until every task gets to this call, no one goes forward. And this is how you synchronize between the tasks. Let's say I want to write out data to a file. But I don't want to write it until everyone's at the same point. I'll put a barrier before I call the write. The next simplest one is the broadcast. One task is I'm broadcasting to you. I'm speaking, you're all listening. That's a broadcast. Scatter. Now it's getting a little bit more difficult. Because now what's happening is one task has a lot of data. But it wants to distribute it across all the other tasks, but not the same data. So the first two numbers go to the next task. The next two numbers go to the task after that. The next two numbers go to the task after that. And here's some simple diagrams of what I'm talking about. If you look in this direction, you can think of that as your memory space, your data. You have a vector. You have multiple numbers. These are the tasks. So in a broadcast, I have this one number. I send it to all the other tasks. Now all the tasks have this number. What's called a scatter, task 0 has this vector. It has 4 numbers. And it wants to send one of each to the other tasks. So it keeps the first number. The second number goes to task 1, because we start counting tasks as 0. The next number goes to task 3, and so on. And so it's basically taking this vector and distributed it across the array. You do this a lot when you're doing input. If you're doing serial input, let's say I read in a data file, task 0 reads it in, but it has to distribute it to all the other tasks. Well, it doesn't send the whole data file to all the other tasks. It only sends the parts that they need. Whoops. Okay. Scatter is just going in the other, well, Yeah, scatter is going in that direction. Gather is going in the other direction. So gather is, I gather data from all the different tasks to a local task. So this data is spread out across these 4 tasks, and 0 wants it all, so it calls a gather, and then 0 gets all the data in one data object locally. So scatter and gather are sort of the same thing, just in opposite direction. Now, anytime you see all on an MPI command, in general, it's this operation followed by a broadcast. So you can think of all of this information. Actually, this is an all scatter. All of this information is, well, no, it's a gather. All of this information is collected here into this data on task 0. And then this data is broadcast to all the others. So it's one of the regular collectives followed by a broadcast of data. And all to all, this is the most general MPI call, I guess you can make, or the most complicated one. Because basically, this is a call where you set it up so each task can send data to multiple other tasks. And so also that means this operation is never really optimized very well, and so it's incredibly slow. And if you can, you should always avoid it. It's kind of like everybody in the room talking at once, and you trying to pick out 3 different conversations from, say, 20 people. Yeah. Oh, this is just what I talked about earlier in the same picture. There's another important operation called reduce. This is a reduction. So a lot of times I want to know what's the maximum value across the data, across all the tasks, or what's the sum total of all the data. Let's say I'm doing, I used to do astrophysics, so one of the big things in astrophysics was mass. So if I'm simulating a star, at some point I want to know how massive is it? How much mass is there? And so this is what you do. You perform a reduce with a sum to get a total. And the next example I have, there's going to be a reduce in it. You look at the code. Here's just a simple example where you've got this data spread out, you do a reduce with a sum, you get the total here. There's also an all reduce, so it would do this and then broadcast it. Scan, I don't see this often. I mean, it's similar to this, it's just sort of an incrementing reduce. Okay, so we're going to do another example. We're going to calculate pi. So again, if you're still in the compute node, ignore the first 2 steps. Just do the compile and run the code. In this case, you're going to have to enter a number because this is an integration problem, and what you're entering are the number of intervals to integrate over. And so the more intervals you have, the more accurate the integration. If you do something like 10, your match with pi probably won't be that good. Something like 1 billion. You're probably on the logging.
Yeah,
Side by dev again. Try and get that up to 50. Yeah, if it complains about host list, look at your prompt. If it says login 1, 2, 3, or 4, then you need to run idev again and get back into that directory. You're not going to break anything.
Is there space in between MPI and oh,
Wait, in my compiled text, it's with the actual, oh. Oh, wait, no.
No, you didn't name the element. In other words. Oh, it's running. That's.
But I didn't, I did it first, like originally when I tried to do it. Originally when I tried to just do it.
Your last compile, you did that show, but then you didn't give it the name of the output.
Oh,
There you go. There. Yeah. So you can do IV run.
Yeah, you're like,
Oh.
I would
okay.
understand that.
So you can do IV run. But otherwise, you just.
Oh, that's, I did. Oh, so like the turn number.
Okay, so your error is pretty close. So do it again and then like you can
How are you calculating?
I already did it. No, this is
It's an interval.
Does it say that pi is equal to 0 because the error is
I only have 10 notes reserved.
I entered like a 1 zillion. Like,
So yeah, the bigger the number, the longer it's going to take.
well, my question is, when I calculated pi, it got -0, but the error was -3.14.
It says I is -0.
I mean, the only thing I thought I did differently was instead of naming it for I decided
I think you blew. You only had a 4-byte integer in there. You blew my.
I blew it up.
Yeah, that's bigger than.
I was
Because I think I only have a 4-byte integer, so a signed 4-byte integer is only good up to about 2 billion, 4 billion, little over 2 billion. Your number is way too big.
Honestly, all I can do is chicken and meat.
Yeah. It's
So
2 to the 32 minus 1.
how big can I go?
That's it. 2 to the 32 minus 1. You
Like,
can do a billion. 1 with 9 zeros will work.
I think that's what I just did.
that's
Yeah.
pretty much all I need. I was really depressed.
Yeah, I just did it.
Yeah.
Anyways.
Okay.
Oh, yeah, but the error
I'll show you
is.
Okay, so what you're doing here, there's this function that's an arctangent, and if you integrate it from 0 to 1, you get pi. So you're basically doing an integral. And the number is just the number of intervals. And what's happening is you're decomposing these intervals over multiple tasks.
So just like Siemens.
Hmm?
So we're just doing Siemens sums.
Yeah. But,
so good.
yeah, and so it's like, say, the first 2 are done by the first task, and so on. And so this is a common example you see in parallel programming pi, because it's pretty easy to subdivide. And we have OpenMP examples. We have OpenMP plus MPI examples, because you're subdividing in one dimension.
It's like a bread, but not really. It's just boiled. It's like mashed potatoes. Think of like grainy grits.
I mean,
It's like grits, but not really. It's like grits, but it's harder. You can dip it.
Oh.
What?
Think of grits and like dip it in.
Oh, we're not. Oh, that's what they're talking about. Yeah, sorry.
That's okay.
Oh, sorry. I thought they were.
Yeah, I thought they were still doing something over there, sorry.
No, I mean, we're about done. I mean, so, summary. I taught you very, very, very basic stuff. I've exposed you to MPI, which most of our training, that's what we do. We're just exposing you. I mean, takes a while to learn it, and you really don't learn it until you write a program, and it fails, and then it fails again, and then it fails again, and eventually you sort of get the hang of it, and when it fails, oh, I know why that happened, and then you fix it. But these are just some of the key routines we covered. Not everything can be parallelized easily, simply, or at all. And a lot of times you'll do this and it will be slower. You'll think, but I'm using 8 cores, it should be 8 times faster, and instead it's 3 times slower. Because all this communication and all this bookkeeping takes time and effort for the processor. And so if you don't have enough work in between these calls, then, especially when you go to really large scale, then the communications and the synchronization overwhelms the rest of the processing time. And so when that happens, you have to rewrite your code or reanalyze your algorithm. Sometimes you can change your algorithm into something that may be slower, but it parallelizes better. And so then you win in the long run because you use more tasks. Some references, and I have to give these slides to John, and he'll share them with the rest of it. Any questions? I think we're done. Thank you. So, what do y'all do now? Go back to the dorm? Go party? Oh, you have to go back to the dorm?
Yes. Well, actually, no, let me rephrase that. We have to go back to the bus.
Oh, there's a bus that's coming. Okay.
We don't finish that 4:30 bus. We won't be home until like 1:00.
Oh, you're catching. It's every hour.
Every hour. So if you miss the 4:30 bus.
Yeah, oh, I was like, y'all keep going. Straight chilling.
What's it called? What's it called?
What's it called? Cassava.
What is that originally?
But they eat cassava too. It's actually called,
No. Yeah, it's going
looks like that, and it's all stretched. I think it is some kind of. Okay, there's